Hello. So we've been working with definite integrals, and we found that they're a great tool for computing area in the plane. We've done area between the curve and the x-axis, and we've done area between curves. Now, another thing that definite integrals are useful for is for finding the volume of solids whose boundaries are curvy functions. So we're going to start out by looking at a technique called slicing. And we'll practice that for a little bit, and then we'll refine that process to solids of rotation later in this unit. Let's take a quick look at what I mean when I talk about slicing. So essentially, if you want to think about this in terms of the roast beef sandwich that you can buy at Arby's, I don't know if you've ever seen them create the slices of beef, but they take a chunk of beef, they sit it on the slicer, and then they just run that solid through the slicer, and they peel off little thin slices. So what we're going to do is something similar. This shape here that's kind of in the pink or red, this guy right here, that's called a solid, right? It looks almost like a dinosaur's bone or something. And what we're going to do is we're going to slice that up into thin little cross sections, we call them. And just like we took our areas and chopped them up into little rectangles, we're going to chop our solids, our three-dimensional solids, into little cross sections. So this blue part here, this shape right here that kind of looks like a little bean or something, right? I'm going to try and draw it there. That thing there, that cross section has some area, and then just a smidge of thickness, right? Just a smidge of thickness. To compute the volume of that little piece, we just have to multiply the area of the region times the thickness. And just like we had our rectangles, the thickness was always dx. The thickness here is dx as well. So essentially, to compute the volume of this little piece, it's just the area of that thing times dx. And you can see they've told us that the area is labeled a of x. So if we can find a of x and multiply it by dx, we can run this thing through a definite integral, and we can compute the volume of the entire solid. That's our goal. Let me show you what I mean in terms of a formula, and it'll bring a little more clarity to this rambling that I'm doing right now. Are you kidding me? Oh, sorry. I thought my microphone went off. I'm not going to delete it because it's just funny, but let's go on to my clarity. So I was speaking of clarity there, and then I thought my microphone went dead, and sure enough it did, so I had to restart this particular slide. But you can see I still have that picture here, but then below it we've sort of written a definite integral that summarizes our job. If we want to compute the volume of this pink-colored solid, we have to add up, using a definite integral, the volume of all the little slices, all the blue slices. And the way we do that is we integrate a of x times d of x over the interval ab, right? We're integrating from one end to the other. And the hard part about this whole exercise is figuring out what the formula for a of x is. So in this video, we're going to focus just on writing an expression for a of x. Throwing it into a definite integral is then just an exercise in calculation. You can have your computer do it, your graphing calculator, or if you're feeling frisky, you can do it using the fundamental theorem of calculus. Okay, so we're going to run through 4 examples where we try to develop the formula for the cross-section area a of x for a particular situation. And this corresponds with number 1 that we have done together in class. Let's take a look, and cross your fingers that my microphone keeps working. Of course, that's only true if you actually want to listen to me talk. So we have this collection of solids that we're going to be analyzing, and in all of the examples that I do in exercise 1 here, there's 4 of them, A, B, C, and D. I'm working on exercise 1. Our job is to find the formula for a of x, which is the cross-section of the solid. So first of all, the colors in our picture are changing roles. The blue is the cross-section of our solid in the plane, but the one that we want to add up is actually the peach or pink. Essentially, we're taking this sphere, which we haven't drawn the entire thing for, and we're chopping it along the x-axis. And the cross sections, as we chop, are these peach-colored circles. So once you have a drawing of your solid, or in this case a rendering, we haven't really drawn the entire solid, what you want to do is you want to draw a picture of your cross section. And draw it in the plane that you're used to seeing it. So I'm not going to try and draw this 3D or anything. I'm simply drawing the cross section because my job is to find a of x. So when I peel this peach circle off of this shape and set it down on the table, it looks like this circle here. And our job is to find the area of that circle, right? We're trying to find the cross section area. When you're finding the area of a circle, you know from geometry class that you're looking for pi r squared. And so what we need is we need a measurement for the radius of this circle so that I can square it and make the formula. To do that, I need to go back to the original picture. And it's hard to see, but if you kind of turn your perspective sideways, you'll see that that radius that I've drawn over in the red picture is actually this measurement right here. And I've drawn it in black here because I already used red. So if you want to make this one black here too so you can see how they correspond, that's how it corresponds. And we have to figure out a formula for that radius. It's not the same for every circle because the circles get larger and then smaller again as we slice from end to end. So we need an expression for that radius. Well, to do that, I'm actually going to draw this picture just in the two-dimensional plane so you can get an idea of what it is that we're actually measuring. So if I were to flatten this thing out and look at it square on, the circle, the blue circle, would look like this. And all I would see of the peach circle that's pointing out at me is simply this line here. And since I've drawn that black line in on the radius of that circle, that would look like that. So from this perspective, you can see that we can calculate the length of that black line. We know that to measure vertical distance in the plane, we do top minus bottom. And we can see those values here. The bottom is pretty easy. That's just the x-axis, so that's a 0. The top is slightly more complicated. That's the y value of this point right here. And to figure out the y value, I have to go up to this relation, x squared plus y squared equals 1, and I have to solve for y. So when you do solve it for y, you actually get two curves. This top curve is y equals the positive square root of 1 minus x squared. And this bottom curve, which we don't need right now, is y equals negative square root of 1 minus x squared, because there's two parts to that square root. So what this tells me is that if I'm measuring that black radius, it's going to be the square root of 1 minus x squared minus 0, better known as the square root of 1 minus x squared. Now I can go over to my formula, and I can pop that in right there. And when you square the square root of 1 minus x squared, you get 1 minus x squared. So my a, and I should call this a of x. Sorry, I didn't use that notation earlier. My a of x for this problem is pi times the radius squared, which evaluates to 1 minus x squared. When you square the square root, it undoes it, and you just end up with the radicand, which is 1 minus x squared. And so this is my a of x formula. I looked at my rendering for my solid. I drew my cross section over here, and I figured out what measurements I needed to compute the area of that cross section. We needed a radius, so I located the radius in the plane, and then I came up with a way to measure it. Vertical distance in the plane is measured by the top y value minus the bottom y value. So we did square root of 1 minus x squared minus 0, better known as square root of 1 minus x squared. We plugged it in right here and then evaluated or simplified that expression. Then we came up with pi times 1 minus x squared. That's how this game is going to be played. Draw the cross section, figure out what measurements you need, go back to the plane, pull those pieces off, write the expression, and then write your A of x. Let's try it with letter B. Now that you've seen the process in action, things should go a little faster, more smoothly. So here the cross sections are squares. It's important to read the directions so you know what shape you're actually dealing with. Don't trust your eyes. What they're telling us is if I pull this peach-colored shape and draw it out flat on the plane, I'm going to get a square. And from geometry class, I know that the area of a square is side squared. The real question is, how long is one side? So I have to go back to the original picture and figure out where this black side is in the picture. It's actually this distance here. Now that's all slanted and weird, so let's draw that flat and see if we can figure out how far that is. Remember that circle from the last slide? I'm just going to draw it again. Right? Now I'm looking at it as a straight-on perspective, not this slanted view. This is the x-axis, this is the y-axis. And that's all shaded in, right? This is the shaded in circle there. My black line goes from this curve here all the way down to the other side this time. So remember, we said that we had to do top minus bottom, and we're going to do that here again. The top one was the square root of 1 minus x squared. It still is, right? The bottom one is negative square root of 1 minus x squared. We did that calculation on the last slide. And when you perform that math, you end up with 2 square root of 1 minus x squared for the distance of that black segment. That means that our side is the square root of 1 minus x squared, 2 times the square root of 1 minus x squared. So over here in my A of x calculation, I'm going to insert 2 square root of 1 minus x squared in for s. And remember, you have to square that thing. And when you square that, make sure you square, oops, my equal sign just got totally messed up there. Make sure you square both parts. So I have to square the 2 to get 4, and I have to square the radical, and from there I get 1 minus x squared. So the A of x formula for this situation is 4 times the quantity 1 minus x squared. I went a little faster on that one because I talked too much on the last slide, basically. But I don't think you need as much explanation. And if you do, you can always pause or rewind. But this is the gist of how you do these problems. Let me knock out the last 2, and then, of course, you're going to try problem 2 on your own. Oh, man, is this thing still working? Mondays are the worst. All right, hang in there. Let's go see another one. All right, the microphone's still working. We're on letter C now. And this is a humdinger, so we got to be careful. The cross sections are squares with diagonals in the plane. So the diagonal is this measurement here that we've been using before. So we just have to be careful. When we draw our cross section for our squares, the black measurement that we've been using is actually this measurement. And then note, they gave us a little hint about squares and their diagonals. The length of a square's diagonal is the square root of 2 times the length of the sides. In other words, if you want to find out how long the side is, you have to divide by the square root of 2. Okay. So first of all, we have to remember how long this black piece was. We did top minus bottom in the last slide, remember? We had this picture here. I drew the blue circle with the shaded region. Then I drew the black segment from there to there. Top minus bottom was square root of 1 minus x squared minus negative square root of 1 minus x squared, which is 2 square root of 1 minus x squared. That's this distance here. That's x squared, sorry. To figure out the side length, since that is square root of 2 times the side, I have to divide by the square root of 2. So I'm going to do 2 square root of 1 minus x squared divided by the square root of 2. Now, hopefully you can do this math in your head, but 2 divided by the square root of 2 is actually just the square root of 2, square root of 1 minus x squared. That's how I'm going to write it. Okay. Now, how do we find the area of a square? Well, it's just like the area of the last square. We have to do side squared. Right? We're going to square the side. And since I just mentioned that the side was square root of 2, square root of 1 minus x squared, when we square this thing, we get square the square root of 2, you get 2. Square the square root of 1 minus x squared, you get 1 minus x squared. So you can leave it as 2 times 1 minus x squared so that's in the same form as the other problems. Or you can distribute the 2 if you want. I'm just going to leave it like this because that's what I did in the other slides. So we had pi times 1 minus x squared. We had 4 times 1 minus x squared. Now we have 2 square root of 1 minus, or 2 times 1 minus x squared. Okay, there's one last example that we're going to work on, and then I'll get you out of here. Finally, for letter D, our cross sections are equilateral triangles with the bases in the plane. So when I pull that cross-section shape off and draw it in the two-dimensional plane, it looks like an equilateral triangle. I'm going to try and draw an equilateral triangle. Those are supposed to all be congruent. Sorry if they don't look congruent. Remember, the base is in the blue plane. That means that the measurement we've been making, 2 square root of 1 minus x squared, and I'm just going to skip ahead to that because we've done it 3 times in a row here. This is 2 square root of 1 minus x squared. That's this distance here. 2 square root of 1 minus x squared. Okay. Now, to find the area of a triangle, remember from geometry class, we need area equals 1/2 base times height, right? Remember this guy? So we know the base is 2 times the square root of 1 minus x squared, but how in the heck tall is this thing? Well, because these are equilateral triangles, this angle here is 60 degrees, and this one is 30 degrees when we drop the altitude. So I happen to remember my special right triangles. I'm going to avoid the Pythagorean theorem and just use my special right triangles. This segment here is half of the base, so that's the square root of 1 minus x squared. And this up and down segment here is the square root of 3 times that. So it's the square root of 3, square root of 1 minus x squared. That's the special right triangles. You can pause the video and go research those if you can't remember them. But when you come back, we'll finish the area formula. So the area A of x is going to be 1/2 times my base, which is 2 square root of 1 minus x squared. Ooh, that handwriting is terrible. It's getting late on a Monday here, and I'm writing sloppy. So it's 1/2 times the base times the height, which we just mentioned was the square root of 3, square root of 1 minus x squared. And when we simplify this, the 1/2 times the 2 reduces to 1, and the square root of 1 minus x squared times the square root of 1 minus x squared is just 1 minus x squared. So I'm left with A of x equals the square root of 3 times 1 minus x squared. So if you've been paying attention, you probably noticed there's a theme for all of these A of x's. It has to do with the fact that all of our bases were in that circle that's in the plane there. So we got 1 minus x squared quite a few times. Okay, this was supposed to be an introduction to slicing. We have known cross sections. Our job for this problem was simply to find A of x for each of the 4 solids. Once you find A of x, eventually you're going to be asked to find the volumes. So let me review that with you one last time, and then we'll get you on to your homework. So just to summarize the process here, once you have A of x, you're going to dump that thing into a definite integral, and you're going to integrate it. The A and the B are the boundaries on the x-axis of your solid. So in our examples, they were all -1 to 1 because the blue circle went from -1 on the left side to 1 on the right side. So you always integrate from left to right when you're going along the x-axis. So those a and b's, those are the boundaries of our interval. Those are our numbers. And then a of x is the formula that we found. You just dump them into a definite integral. And for what we're doing as we introduce this concept, you're just going to crank it out with your graphing calculator. No need to do the fundamental theorem. This last little box down here just summarizes how to get all the way to the volume. We do need a sketch of the solid and the typical cross-section. In this video, I tried to give you the sketch of the solid, or at least the mock-up for the solid, and then I drew the cross-section. From there, we found the formula for area, a of x. We had to get that area formula in terms of x so that we can eventually do the last two steps, which we didn't do in this video, which are to make sure we know the limits of integration and then do that definite integral. Now, my notes here say use the fundamental theorem, but for our purposes as we start this, go ahead and just dump it into your graphing calculator and have the calculator compute the definite integral for you. I hope this gives you an introduction to slicing. You're certain to have questions, and that's okay. When you do, you know where to find me. In the meantime, take care.